You ever stop and wonder why steel is strong enough to build a skyscraper, but, a piece of glass just shatters if you tap it the wrong way? Well, it turns out the world all around us is built on materials with these incredible hidden secrets. And today we're going to uncover one of the biggest ones.
So let's kick things off with something we all know pretty well, the car. It's the perfect place to start. It's an amazing collection of all kinds of different materials, and every single one was chosen for a very, very specific job.
And just how complex are we talking? Well, your typical car is put together from about 15,000 individual parts. Yeah, every single nut, bolt, panel, and wire has been meticulously picked out. And here's why that choice is so critical. Get this. If engineers can save just 1 single cent on each of those parts, maybe by picking a slightly different material or a smarter manufacturing process, they can slash the total cost of the car by $150. The stakes are just incredibly high.
All right, so let's pop the hood, so to speak, and start digging into the material secrets hidden right inside our car. A car is basically a masterclass in material trade-offs. You've got the body, right? It's made of steel because it's strong and pretty easy to shape. But then you look at the bumpers. They're plastic, which makes them lightweight and keeps them from rusting. Of course, you need hard, see-through glass for windows. And more, you're seeing aluminum sneak in to replace steel, all to squeeze out a little better fuel efficiency.
Which really brings us to the central mystery here. Why? Why are these materials so fundamentally different? What is it that makes one thing bend when you push on it, while another just shatters into a million pieces? The answer? Well, it's not obvious at all.
To figure this out, we've got to start thinking like an engineer who's trying to choose exactly the right stuff for the job.
And the contrast here is just night and day. On one side, you have metals. They're strong, they're ductile, which is just a fancy way of saying you can shape them without them breaking, and they conduct heat and electricity. Then on the other side, you've got ceramics, like glass. They're really hard, but they're brittle, and they're insulators. They're like two completely different personalities.
So the answer to our little mystery, it's not something you can just see by looking at a piece of metal. To solve this, we need to zoom in. Way, way in. All the way down to the level of individual atoms.
And this brings us to what you could call a metal's atomic blueprint. This is the secret source code that basically dictates everything about how it's going to behave.
You see, when metals cool down and solidify from a liquid, their atoms don't just bunch up randomly. No, they arrange themselves into these beautiful, orderly, repeating patterns. It's called a crystal structure. And honestly, the best way to picture it is to just imagine a bunch of tennis balls packed perfectly and neatly inside a box.
Okay, so here is our first arrangement. This one is called body-centered cubic, or BCC for short. You find this in metals like iron, and the structure is pretty much what it sounds like. You've got atoms at each corner of a cube, and then one single atom sitting right in the very center of that cube.
Next up, we've got the face-centered cubic, or FCC structure. This one's really common in stuff like aluminum, copper, and gold. So you still have the atoms at the corners, but now there's also an atom plopped down in the center of each of the cube's 6 faces. It seems like a small change, but it's a crucial difference.
And rounding out our big three, there's the hexagonal close-packed structure, or HCP. And as the name kind of gives away, the atoms are packed together in this really neat hexagonal pattern. You'll find this structure in metals like magnesium and titanium.
So here it is, the key point of all this. These tiny, invisible arrangements, BCC, FCC, and HCP, they're not just some abstract geometry lesson. They determine almost everything about how a metal is going to act in the real world.
Which naturally leads us to our next big question. How exactly do these atomic structures control whether a metal is going to bend or just snap in half?
So here's what's actually happening when you bend a paperclip. At the atomic level, entire planes of atoms are literally sliding over one another. This process is called slip. And the perfect way to think about it is like sliding a deck of playing cards.
Now these atoms can't just slide around in any old random direction. Nope. They can only slide along very specific planes and in very specific directions. Each one of those combinations, a plane and a direction, is called a slip system. And here's the absolute key. The more of these slip systems a metal has, the more easily it can deform. It just has more options, more pathways for those atomic layers to slide around. And this table just brings it all home. Check it out. The body-centered cubic structure, the kind you find in steel, has an incredible 48 available slip systems. That means it has tons of ways for its atoms to slide, which makes it super ductile.
Now compare that to the hexagonal close-packed structure, which only has 3 slip systems. With way fewer options for movement, the result is a much more brittle material.
And there you have it. That's the solution to the mystery. The huge difference between a metal that bends and one that snaps. It all comes down to how many pathways its atoms have to slide past each other. And that property is decided entirely by its fundamental crystal structure. It's that simple.
Now, this isn't just some fascinating piece of science trivia. This is the bedrock of modern engineering. It means we can actually design materials right from the atom up.
So, what does this incredible atomic-level knowledge really unlock for us? Where does this understanding actually take us in the real world?
It takes us right here, to the heart of a modern jet engine. What you're looking at are turbine blades. The blade on the left is made of lots of tiny little crystals, all jumbled together. The one in the middle, that's been engineered so all its crystals line up in columns. But the blade on the right, that is a perfect single crystal, grown literally atom by atom. It has properties at scorching hot temperatures that are just worlds better than the others. This is the absolute pinnacle of controlling a material's atomic structure to get unbelievable performance.
So we started with a simple car part, and we journeyed all the way down to the atomic blueprint of matter itself, and we ended up with a single crystal blade that powers modern flight. It just leaves us with one final, really exciting question. What on earth are we going to build next, atom by atom?